Hi, I'm Mr. True. Hey, do you remember in many years ago in math, you used to, when you first learned estimation, they would take like some irregular shaped plot of land, and over that they would put a grid, and they would tell you usually that each of those little boxes in the grid was 1 square mile or square feet or whatever, and you had to count those boxes that were inside, and then go around the edges and count the partial boxes, and maybe if just a piece of the box was inside that irregular shape, it would count as maybe half a unit, and you would do that to estimate the area of that, that irregular shape, meaning it's not like a triangle or rectangle or pentagon. Well, we don't really find areas of pentagons. Maybe a parallelogram or a trapezoid. Well, we're going to start now the second main sort of classic type problem that we have in the beginning of calculus. First one being, of course, derivative to find the area of a curved line along any given value of x, or almost all of them, that worked. And the second one is going to be finding the area of a plane region. Specifically in this video, we're going to be finding the areas bound by a function, the x-axis, and a 2 points along the x-axis. Here's what our problem is going to sound like, or is going to be, excuse me. Use three rectangles to find two approximations of the area of the region between the graph, that graph is going to be y equals negative x squared plus 6, and the x-axis, between the x values of 0 and 2. So we have this boundary along the x-axis between 0 and 2, and so we're looking for, I drew the sort of the entire parabola here, the parabola that opens up downward in quadrant 1, but we're not going to be looking for the area over here in this last little bit, because we're not going to go past 2. Okay, and we're going to do that, like I said, with just old school area of rectangles. And the point of this, of course, is we just did a video about studying or reviewing our skills of the sigma notation and incorporating it with limits. So ultimately, we're going to do this estimation with an infinite number of rectangles, not just 3, but I want to build it up so you understand the basic concept when we are done. Okay, what I did was I took and marked off 0 and 2, and we were asked to estimate the area with 3 rectangles, so I simply took that horizontal distance of 2 and divided it by 3. So now I have 3 rectangles that all have a width of 2/3. So if I have the width, then all I need is to find the height of those rectangles. I can find the 3 areas and add them together. Well, what I have done is I've inscribed these rectangles, so they go up to the very edge of the function y equals negative x squared plus 6. That means that the function is going to define the height of each of these 3 rectangles based on the right-hand side where that rectangle just happens to touch the function. It doesn't matter really that it's the right-hand side. It's the fact that I've inscribed these rectangles, and so I'm using, just the corner of the rectangle that happens to hit that function to define the height. Okay, so let's find the area of the first rectangle. The area of the first rectangle is going to be, I'm going to do height times width, because ultimately I want to get back to that sigma notation we talked about in the last video. So we're going to do the height of this rectangle, which we're going to find by taking 2/3 and plugging it into this function. I'm going to leave a little space because I want to go back to sigma notation here. So we'll say maybe around here somewhere. I'll need 2 lines for this work. We're going to take, let's see here, square bracket. I'm going to put this function in here to identify the height. So it's going to be parentheses, negative, and another parentheses, because you should always use those when you do substitution. We're going to plug in that 2/3. Raised to the second power plus 6. Okay, so there's the height of the rectangle. The width is 2/3. And I'm using these square brackets to just really emphasize where I'm finding the area of each of the 3 rectangles. They're kind of overkill a little bit, but that's why I'm doing it. Second rectangle, we have a height there. Well, now the height again, looking at the right-hand side, we have 4/5 needs to get plugged into this function. Now I'm not going to write 4/5 as x. What I really want to do is highlight the pattern that I'm using as the 2/3 here. Because again, I want to get back to that sigma notation, and we need an index, a counting value. So for this second rectangle, from the original left bound, lower bound, I need to move 2/3 units twice. So we're going to do plus another square bracket, parentheses. Now we're going to plug in that function for the height, negative x, which is 2/3 times 2, whoops, plus the width. So I'm highlighting here that again we moved 2/3 twice. That means this is 2/3 times 1. So height times width. And now the last rectangle. Okay, well again, 1 movement, 2 movements, 3 movements of 2/3. Again, taking that x value, plugging it into my original function here that I have, y equals negative x squared plus 6, and times the width of the rectangle. Now, this area happens to come out, right off the top of my head, of 7.852. Now, you know, why did I teach you summation notation and limits, which we don't need limits for this problem, but the summation notation. Well, let's look at that pattern. What I've done is I needed to take the summation as I starts at 1, and we had 3 rectangles, so we have 3 additions here, 3 terms that we're adding, so the upper limit is 3. And what did we plug in? Well, we plugged in, let's see, we needed f of, let's see here, I don't want to write this. Yeah, f of, and then what did we plug into that function? Well, we plugged in 2/3, but it was 2/3 times 1, it was 2/3 times 2, and it was 2/3 times 3. So what we did basically was, again, we took that over, this will all be summarized in formulas in a few minutes. We took the overall width that we needed to find the area between, we divided it by 3 because we wanted to use 3 rectangles, and we got this width for the rectangles of 2/3. Then, to find the height, I had to start from my lower limit and move by 2/3 once, by twice, by 3 times. So the heights were found by taking 2/3, and the very first height we had to move 2/3 once. Okay, so the lower index starts off as being 1. So the first thing I did to plug into my function was take 2/3 and multiply it by 1, or in other words, to get back to that sigma notation, we multiplied it by I. So we have f of 2/3 I, and the function was the negative x squared plus 6, and then we multiplied that by the width of the rectangle, which was 2/3, and that sigma notation is what we just walked through here to get an area of 7.852. Now, this area, as we can see, is not going to be correct. It's going to be an estimation, but it's not going to be correct. And it's actually going to underestimate the area between the curve and the x-axis bound by the values of 0 and 2. We can see there's empty spaces here. So what if instead of inscribing the rectangles, we circumscribed them? So we're going to start here. Basically, we're going to let the left side of the rectangle be defined or touch that function, and then draw the rectangles like this. And we're going to develop this idea of lower and upper limit. We're going to underestimate and overestimate the area underneath the function. Now, when you use the right corner, you're not always going to underestimate the area, and as you can see now, I'm using the left corner of my rectangles to define their height, and I have some extra area, so I'm going to overestimate the area. So it's not always the right side underestimates and the left side overestimates. It's just because my graph is falling to the right. If it was rising, then it would just the opposite, so as far as the what corner of the rectangle would over or underestimate the area. But I'm getting a little ahead of myself here. So now we have 3 rectangles, and let's write this out in multiplication longhand form and then go back to the sigma notation. Okay, so this first height of the rectangle is defined as at the function. It's still defined by the function, but it's defined by plugging in the value of 0 because it's at 0, that left corner that's touching the function now, not the right-hand corner. So we need to do negative. Now I want to do this a little bit differently here. I want to still focus on the fact that we're moving or breaking the x-axis by values of 2/3. So we need to do 2/3 times 0, okay? So we're going to do 2/3 times 0 squared plus 6. Did you catch why I'm doing that? Because I need the value of 0 to go into this function. I'm looking at x equals 0. So I need my expression to show that I'm plugging in a value of 0 into the function and not 2/3. Why am I doing this times 0, 2/3 times 0? Why am I not just plugging in 0? Because I want to show you the difference between the first problem when the rectangles are inscribed and the second example where they're circumscribed. And ultimately, we're not going to do this longhand arithmetic for every single problem. We need that sigma notation because we're going to bring back in the idea of limits here in a few minutes. So 2/3 times 0 squared plus 6 times 2/3. It's still the width of each rectangle. Kind of taking up too much space here, so I'll just start my second line now. The second rectangle, its height is defined by 2/3. So we're going to do negative 2/3 times 1 squared plus 6 times 2/3, its width, plus negative 2/3 times 2 squared plus 6 times 2/3, and I'm for some reason really writing quite large. This area comes out to be, right off the top of my head, I'm putting my negative in the wrong spot here. Started writing faster and messed up a little bit. Okay, so that comes out to be 10.519. Okay, now the pattern for this is the summation as I starts at 1 and goes to 3 still. Now I know the lower index of sigma notation or the summation notation doesn't have to start at 1, but it will need to start at 1 so we can use those 3 formulas. The summation for when we're taking the summation of I squared and I to the third, because again, we're not going to do all these problems longhand. We're going to ultimately put in an infinite number of rectangles to get an infinitely accurate estimation of the area below the curve, which means we need to bring in the idea of limits, which means again, for the how many times now we need that sigma notation. So we do need to start that at 1, which means that we're going to take and write this in sort of the idea of what we did with the function. We took 2/3 and we did not just take 2/3 and multiplied it by I. You see here, this in the original problem, we did 2/3 times 1, 2/3 times 2, and 2/3 times 3. Well, now all those values that we're multiplying 2/3 by are 0, 1, and 2. They've shrank by a value of 1. So we need to do f of 2/3 times I minus 1, close the parentheses, times 2/3. Now, we know that the actual area is between 7.85 and 10.519. Let's see what happens. And it's a little bit of a spread here. That's not a really great estimation. Let's see if on your own you can do the same problem with 6 rectangles. For this second example, I'm just going to sort of step out, well, I'll rewrite the question, and step out and sort of reveal the solution in small sections and not really talk because it's the exact same process. It would be a good idea for you to stop the video and change the 3 to a 6 and do this estimation on your own. It's going to be the exact same process. Of course, the numbers are going to be a little different, and we are going to get a tighter interval of the area. This will go a lot quicker because I'm not going to talk to this next example. However, I really think it's strongly suggested that you attempt the next section or the next example on your own. We're going to do 6 rectangles instead of 3, and then do a little bit of definitions, defining some processes and some limits, and then do not not a rough estimate like we're doing with the 3 and the 6 rectangles, but an exact estimate that we're going to do by letting the number of rectangles go to infinity. Okay, let me get out of the way and get that other problem up for you. Okay, so what I've done is simply change the 3 to a 6, and you can already tell by the picture that we're not going to underestimate as badly as we did before, nor is our estimation, our overestimation, our upper limit going to be as off as it was, because these spaces are all now smaller using 6 rectangles instead of just 3. Now as you attempt the problem and I reveal it on the board, let's not forget that we were looking for a boundary between 0 and 2. That's a length of 2, and we want to estimate it with 6 rectangles now, not just 3. So I've marked off intervals of 1/3 as opposed to 2/3. Yes, 2/3. And sorry about that. And also note, as you try and do the problem finding the lower and the upper limit, or boundary, whatever you want to call it, that you know, we're marking off not only of our rectangles a width of 1/3 now as opposed to 2/3, but when we go in steps to find the heights of these rectangles, finding values to plug into our function of y equals -x² plus 6, that we're going to be stepping in intervals again of 1/3 as well, not 2/3. So let's get out of the way again and reveal that answer to you as you attempt it on your own. Okay, I hope you got it. We have a lower sum of 8.63 and an upper sum of 9.96, getting closer to the actual estimated, or well, it's going to be estimated indefinitely accurate. So I might just say it's getting closer to the actual area underneath the curve and the x-axis between the values of 0 and 2, tighter now. Okay, so I want to emphasize a couple of things. As you saw, I was highlighting that we were finding the heights based on either the right or the left upper corner of the rectangle. I don't want you to always think that if you're working with the upper left-hand corner, you're going to find the upper sum where you're overestimating the actual area. And if you're using the upper right-hand corner, you're finding lower sum. I just want to emphasize again that that is only the situation we have here because our graph is falling down to the right. If it was rising up, you would have just the opposite relationship there. So don't get that memorized in your head and think that's you know, the end-all be-all. The 1/3 that you're seeing here, we're about to get to the definition. So that 1/3, that width of that rectangle, I verbally said it a couple of times, is going to be identified though with the variable of delta x, the change in x. And the change in x, or the width of those rectangles, are going to be found by taking the upper boundary that we have on the x-axis. Could be the y-axis. We're going to do one of those in the next video. The lower limit, we're going to subtract those again and divide by n, the number of rectangles you'd like to use to estimate the area. Okay, so we see that with 3 rectangles we have a certain estimation, lower and upper sum. With 6 rectangles we're getting closer, but still a little bit of a fair gap there of whatever that is, around 1.3 units. So now we're going to let the number of rectangles expand to infinity. So that means that we need to get some definitions down that I have not yet given you, and then finish up this example after those definitions. And I got one more example to try on your own as well, just like we did here. Okay, let me get this board erased and get those definitions and theorems and whatever you want to call it up there for you. Bam!